And then tomorrow's is your third unit exam in room 101, and then Friday we're back at it in this room, and I'll hand back your graded exams, and we'll just kind of go from there, okay? All right. So one last topic, and actually this topic, the sheet I gave you Monday says that this topic you'll actually have opportunity for extra credit. So this down here, this map of your exam, 11 and 12, that's actually this topic right here. It's great. So let's see what you guys think. But we've been talking about two types of compounds, so you're going to want to kind of review that for your exam. We have molecular compound, which has at least, no, excuse me, molecular compounds have no metals. Ionic compounds have at least one metal. And we use chemical formulas to represent both types of compounds. So we could do, for any compound, we could do this sort of calculation, and it's called a percent elemental composition. And basically, you look at the formula for that compound, and you come up with what sort of weight percent is brought to that compound by each element. So I'm going to kind of walk you through that problem. So of course, to work this problem, you're going to need your periodic tables. Mine go. And a calculator. Okay. So let's just jump in and do an example. So acetone, an acetone molecule, it's a molecular compound. There's no metals in it. Hydrogen's considered a nonmetal. Acetone molecule has 3 carbons, 6 hydrogens, and 1 oxygen. And you need to come up with how much weight is brought by the carbon by percent, how much weight percent is brought by the hydrogen, how much weight percent is brought by the oxygen. Now, granted, there are 6 hydrogens, but they're pretty light, right? There are 3 carbons and, I guess, like I said, one oxygen. So there's a couple different ways to work this, but you have to show all of your work to work it. And I'm going to show you what I call just a 1 mole basis. So we said you can come up with the molar mass of a compound using the periodic table and the decimal number for each element. So the molar mass of acetone is 58.08 grams per 1 mole. So if we consider 1 mole of acetone, we could actually then break down the grams of carbon, grams of hydrogen, and grams of oxygen. And it would look like this. The grams of carbon in 1 mole of acetone would be 3 times the decimal number for carbon, 12.01 grams. The mass of hydrogen would be the number of hydrogen atoms there are, 6 times the mass of 1 mole of hydrogen atoms, which is 1.008 grams per mole. And there's 1 mole of oxygen, because the little subscript for in the formula, of course, is 1. And so we can know the mass that's brought by oxygen by simply taking 1 times its decimal number, 16.00. Now, of course, once we have those relative masses, each element, all we got to do is divide by the entire mass. It's almost like a mixture, okay? So it looks like this. So for carbon, we could take that 3 times 12.01 and divide that by 58.08. Of course, that hopefully you recognize the 58.08 is the mass of an entire mole of compound. So the 3 brings no uncertainty. So rounding wise, it looks like we are allowed 4 significant figures, and that's what you're going to see in the percent. Notice that if we were to, and we talked about this earlier in the class, if we stop right here, that would give mass fraction. But if you take mass fraction times 100, sometimes I put 100%, that gives you percent. So you should get in your calculator 62.04%. That's the weight that's contributed by the element carbon in acetone. We can do a similar thing for hydrogen. We'll take 6 times its mass, 1.008, and divide it by the mass of the entire molecule, which is 58.08. Again, it doesn't work just to plop down a number when you work these. If you're going to work them for extra credit on your Unit 3 exam tomorrow, you have to show your work. Again, I got 4 sig figs, so rounded to 4 significant figures, I got 10.41%. Now sometimes students, if you're with it, you're like, hey, I can get that oxygen by subtraction, and you can. Okay, but let's go ahead and continue this process. There was one oxygen atom, 1 times 16.00, divided by the mass of the entire molecule, which is 58.08, times 100 for 100%. Rounded to 4 significant figures again, and voila! We have a weight percent brought by that one oxygen atom in that molecule, or 1 mole of oxygen atoms in that 1 mole of acetone molecules, 27.55% by weight. So if you're like, now those should all add up to equal 100%, you are right. It kind of reminds me of the egg that we did in your measurements lab, just way back when, the earlier part of the semester. If you're doing a check like this and it doesn't add up to be 100%, no worries, because it could have just been rounding, but it should be within probably plus or minus, I don't know, 0.1. All right. So this actually will be for extra credit. Goodness, this semester is just chock full of extra credit. Okay. I'll give you a look at what this is. Not only for extra credit, but it will help you do that problem on your test, which I encourage you to do. The other thing is that it is an odd problem. Not as in odd strange, but just odd. So you have the answers in the back of your book. 81. There you are. No? I thought I saved it. There you are. Okay. Yeah, it looks like this. I found it. So there's 4 of them. You know, you could do, if you wanted 5 extra credit points, you could do 2. But for 10 extra credit points, you can do all 4. So basically, you'll have a weight percent for A, you'll have a weight percent for carbon, weight percent for hydrogen, weight percent for oxygen. They're kind of fun if you like doing your calculator. So the last topic I want to do is this idea of formulas. Oh, skip the next problem. Okay. And does that bring you to this if you skip 2 slides? That look right. So the last thing I want to talk about, you know, you come into this class and you have the idea of a concept, or excuse me, the idea. You have the concept of a compound. We've talked about 2 different types of compounds. Of course, you use a chemical formula to represent the compound. The formula for water is H2O. Formula for acetone is C3H6O. So the deal is, though, is there are, broadly speaking, 2 types of formulas to represent compounds. There is, I guess I should, yeah, there is the molecular formula, and to me that gives the real number of atoms of each type of element that are in that repeating unit. And then there's a reduced version. I call this empirical formula a reduced version. So I'm going to take an arrow from the molecular formula to the empirical formula, and I'm going to write the word reduced. Now, I probably get the term reduced from math, that like you can reduce a fraction, like 4/2, you can reduce it down to 2/1, that sort of thing. It's a very similar thing. So an empirical formula basically is sometimes reduced version of the molecular formula, in which you have the same atoms of each type of element in the same relative amounts, but they're at the lowest whole number ratio. So, for instance, this is easiest to show you. So the butane molecule has 4 carbons and 10 hydrogens, C4H10. That's it. That's the molecular formula of butane. We can reduce that by dividing both the 4 and the 10 by the number 2. It sound like Sesame Street right there. Okay, so the empirical formula for butane is C2H5. Water, H2O, is the molecular formula. Notice you cannot take 2 and 1 and divide them by a whole number and get another set of whole numbers. So you're done. So the reduced or empirical formula for water is also H2O. Hydrogen peroxide, I call this my Santa Claus empirical formula. So hydrogen peroxide has, a molecule will always have 2 hydrogens and 2 oxygens, but you can divide the 2 and the 2 by 2, and you can reduce it to H1O1, HO. Okay, so that is the empirical formula of hydrogen peroxide. Hydrazine, N2H4, of course you can divide 2 and 4 by 2, and you get N1H2. My next two are the favorite, one of my favorites to kind of show you. So acetylene, it's got a triple bond between those 2 carbons. So C2H2, we can reduce it and it'll just be CH. We talked, I think, the other day about that molecule of benzene, that cyclic molecule, C6H6. So in benzene's case, you can divide 6 by 6 and you can get, C1H1 also. My point is going to be is that actually for these 2 very different compounds, they have very different molecular formulas, different properties, blah, 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 but they reduce to the same empirical formula. I think that's pretty cool. They both have, relatively speaking, 1 carbon for every 1 hydrogen. All right. So, I don't know if you'll buy this, and actually if you go on into chemistry and take general chemistry, we'll talk about a sort of problem where you can go back and forth between the weight percent of a compound and its empirical formula. But the weight percent problem we just talked about, like the relative weight percent of carbon, hydrogen, oxygen, it's very similar to an empirical formula in that an empirical formula is reduced relative number of moles. So they are kind of similar, weight percent and empirical formula, and you can go back and forth between each of them. If you got one, you can get the other. Okay. So in the, for instance, in the acetylene and benzene example, the last 2 compounds we looked at on that chart a little bit ago that had the empirical formula CH, they would have the same weight percent elemental composition. Makes sense? So a formula unit, remember we talked about 2 types of compounds, and a formula unit is a repeating unit of an ionic compound. Usually those are already reduced into an empirical formula. There are a couple exceptions, and so I'm going to show you the exceptions, so don't blame me. But remember that mercury 1 polyatomic cation, that's Hg2+, just drives me nuts, but you're going to want to know maybe for your test on tomorrow. But you guys would tell me that mercury 1 chloride looks like this. Again, just to kind of remind you what you're going to be running into. If I give you the name, what I would suggest, and I tried to emphasize this in the problems, is I would rewrite it. I would take my mercury 1 and I would recognize that that is Hg2, 2+, that's mercury 1. And then I would write my chloride. I would find chlorine on the periodic table. I know it's a 7A, might even have a -1 at the top there. I would write Cl -1, and then I would crisscross. So if we crisscross, of course, the number of Hg2s we need is 1. So Hg2 just comes down like that. And the number of chloride ions we need is 2. So that's just kind of a little review of what we did in lab. So the point here is that if we were to reduce that, of course, you can divide each of those 2's by 2, and the reduced formula would be HgCl, which is a different cat. How do I say this? Well, it just is. I mean, the mercury 1 chloride, it's Hg2Cl2, but its empirical formula is kind of a queer-looking thing. Another example is something, another example would be ammonium nitrite. Again, just to kind of remind you what you should be reviewing for your test tomorrow. Ammonium is NH4 plus 1. Nitrite is NO2 minus 1. Okay, so if we crisscross, we're going to get one of each. So that's actually what you see down here. We have one of each, ammonium nitrite. Now, the fact that you actually have a nitrogen here and a nitrogen here, that's really what? N2H4O2. Now, this looks weird. I mean, you actually can find that on the internet for ammonium nitrite and everything. This actually brings significantly less information than this, but it's true. So with that in mind, of course, since we have 2, 4, and 2, we could divide everything by 2 and end up with the empirical formula of NH2O2. NH2O. So those are just kind of some weird examples. They don't really make sense when you go back to the compound itself, but it's an empirical formula. So these will also be due, I should say, for extra credit. And let me just take a look at that again with you. So 81 was one that you've seen, but notice the special instructions for these. These will be 10 extra credit points if you choose to do them. These should take you maybe, I don't know, 2 minutes. Because all you got to do is reduce them if possible and write the empirical formula. So here's what that looks like. Maybe. So the first one, you can reduce it, right? Second one, you can reduce it. I'm thinking D up there. Does it look like you can't reduce D any further? Yeah. So D is a good example of that's the molecular formula, and the empirical formula would be the same. So on your test tomorrow for extra credit, I don't know how much. Did I say how much? For extra credit, I have 4 points. You can go ahead and reduce the formulas I give you to their empirical formulas. Okay? So, very good. Yeah, I forgot. This test tomorrow has got the whole ionic compounds and Lewis structures. It's on your, okay? I think I kind of outlined this on Monday, and I put it on the board. They're kind of grouped by, so. Okay. Very good. That's all I have today. Thanks for coming.